We're okay.
All right, let's get the lights on. Better? All right. Good afternoon, everyone. Thank you for coming. So this is sort of a second talk of three, where the three talks all put all together kind of gives you a report on the status of fundamental physics, the physics that looks into the deepest secrets of nature, if you will, in the sense of how space and time works and what are the subatomic particles and all of these fundamental questions. And you know, subatomic particles on the smallest possible scale. While general relativity, on one hand, discusses things at a very large scale, because gravity is such a weak force, so we don't really detect it unless you go big. But when it comes to the subatomic particles, the electrons, the things that you're more familiar with, then there is an entirely different, completely different set of paradigms. It's like so completely different that people are having trouble to this day for the last half century trying to reconcile them together. They're very different. So this is what I will talk about today. And then in the third talk, I will discuss the current attempts at trying to reconcile the first the two things together, which are in the hypothetical realm. Everything that I discussed last time and everything I will talk about today, or almost everything I'll talk about today, has been experimentally verified, and we know that works quite well. So the story begins in the early 20th century when people suddenly realized that Newton's laws don't work. I mean, 300 years after Newton's greatest contribution to science, and all of a sudden we try to apply it to things that are below a certain size scale, and we find that it doesn't work. F equal to ma has to be thrown out. So everybody who's taken modern physics or quantum mechanics knows that the structure of the theory is so very different. It's an entirely different mindset. For example, in ordinary mechanics, ordinary classical view, people think the most important things that describe nature are the position of an object and how fast it is going. It's as simple as that. But these notions become very fuzzy in a very small scale. You can't really define them concretely, exactly. You can define probabilities, you can define possibilities, you can define different discrete scales, but you can never really pinpoint them. And even if you look at the math, even if you don't know what that is, it is very different from F equal to ma in all of its constituents. The worst that this can be is a second derivative here, but here I have complex numbers, I have derivatives, I have weird things called operators, and it becomes really interesting. It all came out originally based on trying to understand the so-called spectral lines of atoms, so of elements. So when you know that elements shine certain lights or absorb certain lights, you know that they do so in certain discrete frequency. They don't do so like in a continuous way. And the whole story just develops over the first 20 years of the 20th century, and people realized that we have to replace these concrete ideas of classical mechanics of position and time with other things that we call probability distributions and expectation values and all kinds of weird stuff that people take quite some time to understand. This is actually a kind of a picture, quote unquote, of the hydrogen atom, different probability clouds of the hydrogen atom that were taken by these guys in this research using something called the quantum microscope. Essentially, we did quantum interactions with a hydrogen atom, and we came up with this. Right, and so people would say that this is a cloud that describes the probability of finding one electron inside this atom. So if anybody asks you what does an atom look like, even the word look like doesn't mean as you think it should mean anymore. It's kind of funny. The people who discovered this, I mean, everybody knows this. For example, there's Niels Bohr, de Broglie, Heisenberg, Planck, right after he discovered quantum mechanics, you can tell. And they developed the theory in parallel with our understanding of classical mechanics. For example, it is not relativistic. So it doesn't conform with Einstein's theory of relativity. It only discusses the motion of particles or behavior of particles that are slow speeds. Okay? They had to put in extra stuff in order to account for the experiments that they're working with. So the basic mandate of quantum mechanics doesn't really allow for photons, for example. Photons are particles of light, travel at the speed of light. They require relativity to treat them. So they put that as an extraneous condition on quantum mechanics itself to explain how experiments work. Certain mechanical properties of the electrons and particles, like for example something called spin, they don't also show up. So in terms of those of you taking quantum mechanics, the Schrödinger equation doesn't treat photons and it doesn't treat spin. You have to put it as an extra stuff. So, but it was a great triumph nonetheless, because it explained everything that they could measure at the time. On the other side, however, before I go to the other side, let me make a short note on the experimental side of this. And rather than tell you a long story of how experimental particle physics has developed, I'll just give you a little bit of a note on how things are being treated in today's world. Nowadays, remember, we're trying to probe matter at its deepest, and smallest. We're talking about sizes of subatomic distances and so on. We can't see these things. We have to find them by direct means. So people came up with the idea of a particle collider, or a particle accelerator, where essentially they smash atoms and ions together, and they study the debris that comes out. And I always think of it as it's like smashing two Cadillacs just to know how they work. Head-on collision. And the faster you smash them, the more stuff comes out, the deeper you're probing. Which means the more energy you put in these collisions, high energy collisions, the closer or the deeper you're looking. You want to go deep, you want to go at smaller scales, invent machines with larger and larger energy. So these machines are typically very big. So for example, our current most advanced machine is the Large Hadron Collider in Switzerland. I actually was there for a couple of months, did some work. That was the only time in my life I did experimental work, back in the day when I was a graduate student. And it's basically a tunnel, like a huge circle underground, and this is the picture of the tunnel inside when it's off, when it's switched off, and the accelerated particles using very strong magnetic fields, and they accelerate faster and faster and faster and faster, and then wham, they smash them together. The debris that comes out gets detected by these detectors. Look at the size of this thing. There are people out there, right? And there are maybe, 3 or 4 detectors with some fancy names like Daisy and Alice and so on. And this thing, this major accelerator, was the one that is currently the strongest one. And it cost some $8 billion to build back in 2007, and a similar number to run every year. So it's pretty costly experimentation. Well, that's all I'm going to say about the experimental side of things, because we have a lot of theory to cover in today's talk. I was going to say on the other side, as people were working on subatomic particles in the low regime, Einstein was working on special relativity. And Einstein developed a theory where you can treat particles that are moving faster and faster and faster as close to the speed of light. The theory can discuss photons, it discuss motion, discusses, it equates between space and time, like we said last time, when space and time become one unit. Ordinary quantum mechanics doesn't do that. It treats space and time separately because it's not relativistic. And this is one of the most major equations in special relativity. It says that the total energy of the particle, of a free particle, squared, is equal to the square of its rest energy, equal mc squared, plus a term that depends on its momentum squared as well, which means that the total energy of the particle in special relativity is a square root of these quantities. Remember that square root, we'll come back to it in a second. But this is in contrast with the equation in classical mechanics that you're familiar with, which just says E equal 1/2 mv squared. That's the classical version of this thing. Right? It's not immediately obvious how this comes out of that, but it does. Okay? So this is Einstein's energy. So the next question was, here we go, we have two competing theories, Quantum mechanics discusses slow-moving small particles. Special relativity discusses fast-moving particles. Can we combine them together? Can we put together a theory of relativistic quantum mechanics? And it was this guy, Paul Dirac, famous British physicist, who first discovered relativistic quantum mechanics. He put down a formula that doesn't look like anything we've seen before. It doesn't look like the ones in special relativity. It doesn't look like the first formula in quantum mechanics. But believe it or not, this is the formula known as the Dirac equation that marries relativity with quantum mechanics. Now, finally, quantum mechanics can discuss probabilities and everything just like it normally does, but of high-speed objects. Objects moving at very quick speeds. And at this point, after seeing all of this science done, and after seeing the pictures of all of these scientists, I always ask myself, does physics do anything to one's hair? I think you've noticed Planck, Einstein, now this guy, I don't know. It's a big question that I haven't been able to answer yet. So, one of the major predictions of Dirac's equation is this. Because of the fact that Dirac's equation looks at Einstein's energy equation and takes it into consideration quantum mechanically, you will notice that the energy is a square root, which means that there are two solutions, one positive and one negative. Which means that if you treat this quantum mechanically like the Dirac equation did, Dirac has found that there seems to be two different worlds. The world of positive energy particles, the ones we're used to, the electrons, the protons, the things that we play around with in the lab, but then there's another world that appears in the equation as negative energy states. And he said, how come we don't observe these negative energy particles? He came up with this whole model of something he called the hole theory. Essentially, he said, well, we live in a world where there's just the energy is like a sea, and everything in that sea is filled, but then every once in a while, a particle jumps from a negative energy to a positive energy, leaving a hole behind. That hole is a new type of particle. Dirac discovered antimatter, theoretically, not experimentally. And not so late, a little bit afterwards, after he published all of this, experimentally people were able to generate and detect the anti-particle of the electron in the lab, which carries all the properties of the electron, except that it's positively charged. Has the same mass, has the same spin, has the same everything, but it's positive. This is what appeared in the Dirac equation as negative energy states. Everybody just called it the positron right away. Okay? But we should have called it the proton, but that was reserved for something else. So they called it the positron. And nowadays we know that there seems to be this symmetry of nature where every particle we observe in the lab, there is an antiparticle out there. Some particles, like the photon, they don't have charge, so mathematically they are their own antiparticle, if you will. But there's this clear symmetry between the two. So what is the consequences of this? The consequences of this, if you think about it, the original version of quantum mechanics treated particles individually. So, like we do in our quantum mechanics class. Give me an electron, give me a potential, I'll write down the equation, I'll solve for it, I'll find the probability distributions, I'm good. If you try to do that with the Dirac equation, it's not going to work, because you would be ignoring other solutions. In other words, Dirac's equation is really a not single particle equation. It is a many particle equation. You cannot really treat the subatomic worlds at a relativistic speeds, both quantum mechanically and relativistically, without treating an ensemble of particles all at once. We call it a transition from a single particle theory to a multiple particle theory. This was a big step because it brought in what happened next. Okay? If you slow things down, then yes, you can treat single particles like we do in ordinary quantum mechanics, but that's an approximation because we slowed them down. At high speeds, we have other particles to worry about. But then at the same time, other particles have been discovered as well as people were doing this advancement in theory. For example, it was found afterwards that inside the neutrons and protons there are small particles called quarks, and these quarks come in 6 varieties, and they carry some unimagined names: the up quark, the down quark, the top quark, the bottom quark, the strange quark, and the charm quark. These are the names of things because they ran out of names, Greek names to call things. And we've discovered things like, I don't know, a horde of particles. I'll show you some of them in a minute. But it was starting to become clear that we really have to classify particles, subatomic particles, into 2 major classifications. Some of them behave like photons, for example. They have a property of spin to be equal to 0. Now, spin is a quantum mechanical property. I should have said something a little bit about it before. That appears mathematically as if the particle is spinning around an axis. But I put the words "as if" in quotes because it's not really spinning, but a property that exhibits certain characteristics. Like, for example, it generates a magnetic field as if the particle is spinning. But in reality, it's not really spinning. The best description of spin I've ever heard was one of my professors used to say, look, imagine a sphere that is spinning around its axis. Now take away the axis and take away the sphere. That's spin. What's left is a mathematical description, not an actual spin. Anyways, particles come into 2 varieties and they behave differently. They either have integer values of spin, like 0, 1, 2, 3, and so on. When we calculate the spin, we calculate it in units of Planck's constant. So 0, 1, 2. Or half integer values like 1 half, 3 halves, 5 halves, and so on. Okay? Photon has 0 spin. Electron has half spin. Quarks has half spin each. When you add them up into different combinations, you can generate particles with 3 half spins, for example, and so on. And these are 2 different sets of particles that behave differently. They have very different characteristics, so they gave them 2 different names. The integer spin particles, they call them the bosons, in honor of an Indian scientist by the name of Bose, like the loudspeakers, not the same guy. And he and Einstein developed the theory of 0 integer particles, so they're called Bose-Einstein mechanics, or bosons for short. And fermions, which in honor of Enrico Fermi, the Italian-American scientist who also worked on subatomic particles. So fermions, half integer spins, bosons, integer spins, remember that, that's important. But then the floodgates were open and people were discovering particles every which way. It was for a while, literally they called it the zoo of subatomic particles. Electrons, they're just heavier. A famous scientist by the name of Isidore Rabi once said, who ordered that? Why do we need these particles? They don't seem to appear in atoms, they just appear in particle accelerators. And 3 types of neutrinos associated with each one of the electrons is now a clear discussion. They discovered, these are all fermions, by the way. They discovered more bosons, for example, something called the 2W particles, W positive and W negative, and something called the Z0 particle, which had 0 spin and seemed to behave just like a photon, except that it had mass. Okay? These are bosons that were discovered later. And eventually, they found out what the role of each one of these particles is, so I will say something about that. But in the 50s and 60s, they were just, these particles were being discovered every day and experimentally, and people were trying to develop theories for it. So, how do we apply relativistic quantum mechanics to all of this? That was the major question in the 50s and 60s. And once people realized that you can't treat each particle individually, you have to put them all together in one big mix, we worked on relativistic quantum mechanics, and that's when a new theory was born. It's the one that persists to this day. It's called quantum field theory. Quantum field theory says, well, you can't describe them as single particles because they're not single particles. What you really have here is not particles. What you really have is fields. Fields in the old sense of Faraday. Fields that fill out all space, except they are quantum fields. What's a quantum field? Well, it's a field that has been treated quantum mechanically. I'll show an example of this. And excitations of these fields, like energy levels, are what you and I see in the lab as a subatomic particle. That's how this quantum field theory was born. You can think of just the universe is filled with those fields, where we are those fields, and we're walking through those fields, and just every particle that interacts with every particle, which makes you and I and the rest of the universe, is just excitations, that means exchanging energy, jumping from one energy level to another. It's a big mess. That's what quantum field theory is. And you can give them names. So you can say the photon field, which is just electromagnetic field, whose quantization is the photon. You can say the electron field, which is a field that fills out all space and whose excitation is what you and I call electrons. The quark field, the positron field, every single one of the particles, fundamental particles, can be treated as having its own field. And what we do in the lab is we detect only those fields when they are excited at higher energy levels. If there's zero, you don't see anything. Excitation, nothing. A little bit of a tidbit. People sometimes ask me, why is it we teach the harmonic oscillator so much? Because it's everywhere. Even those fields behave like a great ensemble of harmonic oscillators that are rippling in space. That's the best visual one can give to these things. So what does it mean to quantize a field? Remember at the very beginning, we said that quantum mechanics is based on a funny mathematical thing called an operator. Students taking quantum mechanics will be able to understand what that is. But the point is, it's a mathematical object. It's not a number, essentially. It's a mathematical object. And the people have discovered that to do quantum field theory, all you need to do is to find an expression for the field, preferably relativistic, find a solution to the equations of motion like we do in Maxwell's equation, for example. Expand the solution in an infinite series. For example, a Fourier series. Now, this is not a field. This is just an ordinary Fourier series. And usually, calculations of quantum field theory look like this. Take the solution, expand an infinite series, like we do in E&M, for example, when we expand in the Legendre polynomials or the Fourier coefficient, whatever. We always have infinite series. But then, take the coefficients that sit next to those fields, those functions, which you and I work with when we do mathematics and E&M and quantum mechanics, and make them into operators with certain properties. Once you do that, you've got yourself a quantum field theory. Now, of course, the devil is in the details. And the details here are, trust me, scary. But that's basically what happens. And those operators are the ones responsible for acting on the fields and generating particles. You can calculate things like what happens when particles collide together. Okay, what do you expect? Those equations, based on those infinite series, are the ones that tell you the story, tell you how the energy will be exchanged, for example. It tells you how momentum is going to be exchanged. It tells you how whether a particle will suddenly disappear and another particle will appear in its place. Quantum field theory predicts such behaviors. It predicts that it's possible for two particles to get together, they annihilate in a puff of smoke, figuratively, of course, and another particle comes up. This is acceptable because energy is still conserved, momentum is still conserved. All it did is just changed form from one type of particle to another type. All of this can be calculated using series like that, and we've got, instead of coefficients, numbers, you've got operators in them, and you do the calculations. Okay? So that was the point somewhere 1962 or so. There were some issues, but people were able to handle them. As I said, they only work with infinite expansions, so infinite series. They don't work as a closed form solution. Nobody knows how to do that to this day. Nobody knows how to write down a quantum mechanical field theory without expanding things, which is a pain because you don't want to expand things. You want a closed form result. You don't want an infinite series and then you add up a few terms and stop. You want to add the whole series up. You want to know the full result. To this day, nobody knows how to do that. And non-perturbative, that's what they call it, something that doesn't expand. Quantum mechanical theory doesn't exist, which it could be problematic because if you're adding up different terms of the series, you expect them to get weaker and weaker as you go along the series. You don't want them to get stronger because you only want to add the first few terms and stop. But if it gets stronger after that, then you're missing stuff. They still work with it, and it still gives interesting results, which is really fun. I'll give you an example. So based on this approach, this idea of quantizing a field, we have now 3 theories. Quantum electrodynamics. That's the theory of the quantum electromagnetic field. It tells us how electrons and photons interact together to simulate the behavior of electromagnetism, repulsions and attractions and all kinds of things. There is something called quantum chromodynamics. Won't go into why the name is called chromodynamics, but this is the one that dictates the behavior of the quarks inside. And it predicts the presence of particles other than the quarks inside the proton. They call them gluons, for the very simple reason that they are the particles responsible for holding the quarks together. So they call them gluons. Right? Quarks are fermions, gluons are bosons. And then the last theory is called the electroweak theory, which explains the so-called the so-called weak force inside the nucleus. The only thing I know of the behavior of the weak force, or I know the reason why it's there, is that it's responsible for radioactivity. It's the force that kicks things out of the nucleus and so on. And it's a force that's completely different from the first two. The first two, electromagnetism, and the strong nuclear force which holds the quarks together. Then you've got this third one. And the funny thing is, this theory requires the use of electromagnetic force, and the two of them are bound together into one theory. We call it the electric theory. All of these 3 forces combine together in what we call the standard model of particle physics. They describe the behavior of subatomic particles at high speeds, and they describe the 3 forces of nature that we know works at those scales. Notice gravity is missing. It's the only force that is not in this picture. Next step. There is an interesting discovery found by Richard Feynman in a PhD thesis, in his PhD thesis, for which he won the Nobel Prize. To my knowledge, this is the second time in history where a Nobel Prize in physics was awarded to a PhD thesis. The first one was De Broglie. He said, look, let's take a look at this infinite series of stuff. Each term, these are difficult integrals to do, difficult calculations to do, but he discovered that each term in this infinite series corresponds to a possible particle interaction. A possible one. For instance, what happens when 2 electrons approach each other? Well, they approach each other, there's a force of repulsion between them, they move away. Quantum electrodynamics says that what really happens, quote unquote, is that these 2 electrons exchange a photon. Bam! A photon is exchanged. And because of conservation of momentum, the electron moves away. This is a simple possible interaction. And he writes down a picture like this, where it's explained as electrons coming together, releasing a photon, and so on, and assigns certain rules to them. You take those rules, you put them in mathematics, and you get yourself a result without having to do too much work. But that's only one possible interaction. There are an infinity of possible interactions. Maybe they exchange 2 photons. Maybe they exchange 14 photons. Maybe the photon halfway became something else and then came back to being a photon. Maybe another particle was released. Each one of those possibilities is a term in the infinite series. You add them all up, you get yourself the prediction of a theory. In other words, it's also been described as the comic book form of quantum theory. Because it's all about those little diagrams. Look at these little arrows. These all represent particle interactions. The particles with arrows are fermions, and the particles that are wiggly are bosons, and they exchange each other. There are so many possibilities, things can come up and come down. You add this infinite number of possibilities, and you got yourself a prediction. And by the way, speaking of Feynman, if you haven't read Feynman, I strongly suggest that you do. Whether his physics or his popular books, he was an amazing storyteller, and this is one of his best books. I've read it like 6 times. So look up Feynman's work. So here we are. That is the big picture. This is the mathematical picture. Quantum field theory by now, we understand what's going on. Fermions are the ones responsible for the structure of matter. Atoms are made up of fermions, like quarks and electrons. Bosons are the ones that are responsible for forces. Photons represent electromagnetic force. Gluons represent strong nuclear force. And the W and WZ bosons represent the weak nuclear force. The whole universe, literally, is one big soup of fields where all these particles are interacting. You can look at them mathematically, you can look at them using Feynman diagrams. You've got yourself a calculation that tells you exactly what you found in the lab. So the three forces of nature are described by those. And notice I've written here the particle that's responsible for each one of those forces. Electromagnetic attraction, repulsion, the photon is used. The weak, there are three particles, and the strong, there is the gluon. But of course, I point out that gravity is still missing. Why? Because no one has been able to make it quantum mechanical. I'll skip ahead a little bit. Here's a picture of the current state of the particles that we have. All of these are fundamental particles. The quarks, electron vector, just one among many, muon, tau, neutrinos, and the force carriers, the bosons. And then there's the Higgs boson. I was going to say something about the Higgs boson, but I can skip that, I think. Here are the problems we have with this theory. It doesn't include gravity. Okay, gravity is still described by general relativity, and it cannot be made quantum mechanical. That will be the subject of my third talk. Attempts of combining gravity into this picture. There are certain problematic issues with quantum field theory. For example, some calculations yield infinite results, and people have developed techniques to get around that. It's called renormalization. It doesn't really matter. It just tells us that maybe there's a deeper theory here that we don't quite know yet, and the infinity is mathematics is a way of telling us that there's something here that you haven't yet broken up. It doesn't explain things like the constants of nature, for example. It doesn't say where's the mass of the electron coming from? Why is it that mass? Why is the interaction of particles with that strength? We'd like to understand these things. We'd like to know if these numbers have been chosen by the mathematics for a reason. The quantum field theory does not provide that problem. Other issues, why are there 6 quarks? Why are there 3 kinds of leptons, which are electron, muon, and tau, and so on? All of these are questions that quantum field theory does not answer. However, it is the most successful theory of physics. Quantum electrodynamics in particular, the theory that discusses the quantized electromagnetic field, makes predictions that are good to parts in billions in the lab. It brings out numbers that are really, really accurate. It's considered one of the most accurate theories of physics ever. No theory of physics has ever been able to predict the results of experiments up to that great accuracy. So that is why it's become pretty standard to work with quantum fields. Another problem with quantum field theory is that there seems to be like 3 subatomic forces, let's call them that, but 2 of them are unified. So we know that the weak nuclear force and the electromagnetic force work together in one theory. It's called electronic theory. But why is it that the strong force has been left out? Is there a theory that kind of combines all 3 together? That is the quest for unification, which is a separate thing that people are trying to work on. People have proposed mathematical theories. They're called grand unified theories, or GUTS. And, but they predict things that we don't see in the lab. Or maybe our particle colliders are not energetic enough. In other words, we need to spend more money, that sort of thing. But this is where things stand today. People are just trying to come up with ideas to solve the problems of quantum field theory and try to explain all of these unanswered questions, as well as unify these forces into one. One of the attempts at unifying forces is called supersymmetry, which, what time is it? So I know if I have time to talk about that. What do I have? 5 minutes?
Yeah, sure.
Okay. So supersymmetry is one attempt at trying to unify things. And people like it It's a mathematical structure that says that every boson and every fermion have a sister fermion and sister boson. And that nature can freely exchange one into the other. Makes this into that, and this into that. The reason this is useful is that when you carry this calculation to its natural end, you can answer so many questions. Well, so if you take the current theories that we have, quantum field theory, the standard model, and make it supersymmetric, apply this mathematical structure to it, it doesn't just only explain why there are fermions and bosons, it also explains a lot of things like why are the strengths of the forces the way they are. It answers questions such as some of the constants of nature come up just by using supersymmetry. So it's a very popular thing, but it's very hypothetical, so I'm not going to say too much of it right now. And aside from the fact that these supersymmetric particles have never been found, but that doesn't stop people from giving them names. So supersymmetry is a very popular thing for the reason that that it answers so many questions. But of course, physics is an experimental science. So if you don't see verification in the lab, then you're not really doing physics. That doesn't make people stop working on them. Because it answers so many questions. Can't people get it? Nature could disagree, but people like it because it does answer a lot of questions. It does predict things that we don't see, and every once in a while we build a larger particle collider and try to make it stronger and stronger. Maybe we'll find those elusive supersymmetric particles. Also, and here's the funny thing that I want to conclude with, supersymmetry comes in two varieties. Two types. One of them is called global, and one of them is called local. Local is harder to do. But here's the thing. When you do local supersymmetry, something very strange happens. All of a sudden, gravity pops up. The curvature of space-time suddenly appears in the equations. Where did that come from? I wasn't even doing general relativity. I was doing particle physics. All I did was added an extra symmetry in the calculations, and I called it supersymmetry. And I chose the local variety, and all of a sudden my equations are changing. I'm looking at it, I see curvature of space-time. This has got to be right. There's got to be something here. This just cannot be a coincidence. There's got to be some depth in there, because all of a sudden, something that completely unexpected comes out. That's why people work in this so-called supergravity, which happens to be something I work in every once in a while, where gravity and supersymmetry and particle physics are kind of combined together. And it's one way of looking at things if you want to think about unification. But anyways, I will say a little bit more about supersymmetry on the next talk, because it turns out to be closely related to string theory, which will be the main thing of my next talk. So I'll just summarize by saying that this is the current state of the standard model, the particles that we know, the particles that we don't know, the hypothesized ideas, and ideas that are so beautiful that it really would be a shame if they're not real. Thank you. Any questions? I hope that wasn't too much. I was trying to cover a lot of ground in 45 minutes or so.
I have a few questions. You mentioned at one point that every particle can be described, or is in modern physics described as a field.
Yeah.
Is that, so if we consider the electron, the muon, and the tau, would each of those be a separate field, or would those be different, like, vibrational states of the field?
Fields.
They're actually separate fields.
They're treated as such anyway.
Interesting. But okay, so
because they cannot swing into each other.
But a muon will decay into an electron and a neutrino or something, right?
Sure. And two electrons together will decay into a photon. Will combine into a photon, or a photon can decay into electron and positron.
So these fields,
right?
They clearly couple to each other.
Yes, they are coupled, but they're not the same field.
Interesting.
Yeah.
Okay.
It's like, if you want to think of it in terms of like energy levels, so let's say neutrinos, for example. It's easy to think of neutrinos because these switch with each other. The neutrinos, there's called neutrino oscillations. So if you think of them as energy layers, so it's essentially like just energy is being given to each field depending on where you are.
Yeah.
In a sense. That's what it is.
And then you do a strong distinction between particles that are spin 1/2,
Yes.
the fermions, and then the integer spin particles, the bosons. There's maybe a little bit of venturing into your next talk here, but if you start to think about these particles as strings, is there something topologically different about a spin 1/2 versus a spin 1 particle or an integer spin particle that like some knotted
Yeah, I know
configuration or something?
No, not topology, but you can generate one into the other. The different states of quantum oscillations of the string, but they're not topologically different. No.
Not topological.
They're all open strings, except gravity.
Yeah.
Gravity is the only closed string. But they're all open strings, so they all just look like ordinary filaments. There's no topology difference between them.
Okay.
When they move in space, they draw world sheets as opposed to world lines.
Yeah.
But they're all the same. Yeah.
In terms of the string theory model of these particles, I mean, there's nothing fundamentally different about the structure
No,
of the
that's the beauty
strings.
of it.
Interesting.
It's the beauty of it. The
So,
beauty of
okay,
it is
okay.
it's just one string. One ring to rule them all.
Hmm.
Literally.
Very
Yeah.
Oh, so if you wanted to encourage students to go do research in this field, would you recommend that you have to have a bit of an imagination?
Yes and no. Sometimes an imagination is useful, but sometimes the imagination is not so useful because I have found from experience in that if you try to imagine the unimaginable, it can slow you down.
Yeah.
It does not advance you. Just try to understand the wave function of non-relativistic quantum. Good luck. Try to visualize it. You can understand it, you can mathematically treat it, you do things to it, and you go to the lab and you find that it works. But can you really imagine what's really going on? Can you really answer questions as like, where was the particle before you measured it? No. And if you try, the imagination runs amok, you're getting the wrong answer. So the answer is yes or no. Depends on which situation you're looking at. Feynman had a famous statement. I think it wasn't his, it was borrowed from somebody else. But when people try to interpret things and imagine and visualize and philosophize, he would just say, shut up and calculate. Don't waste your time. Well, you can do it on your own time, but if you really want to advance the cause of science, it's really not very useful. Yeah.
So it's been a long time since I've done anything with the Dirac equation.
Yeah.
And earlier on in your talk, you were talking about negative energy and positive energy. We're also talking about negative charge and positive charge.
Yes.
And protons and, I'm sorry, electrons and positrons. And I got lost in there exactly how negative energy turns into negative charge.
It doesn't turn into negative charge. It's the sea of energy where holes are left. If you calculate the properties of these holes, then they are required to have an opposite charge. But they also have negative energy with respect to the electrons.
So,
but in reality, they actually have real energies, positive energies. His interpretation was wrong, but that's how he appeared in this picture. His original interpretation was not right.
and so the other question that I had, I think, is a very closely related question to the one that Eric had, having to do, so you were asking about electrons and the other two
Muons and
muons
tau.
and tau.
Yeah.
So you had mentioned that electrons and positrons were different fields. My
Yes.
understanding is that they were simply different charges of the same particle, but they're separate fields.
No,
in these.
they're separate.
So they have
They're separate
exactly the
fields,
same-
but there is a symmetry. They have to exist together. But they're separate. Every single particle has its own field in this calculation.
One other question for you, and this probably isn't really the focus of what you wanted to talk about. At the very beginning, you were talking about a quantum microscope, and you showed us these pictures of
Yeah.
hydrogen. I've never heard of a quantum microscope.
Neither did I. I discovered it the other day when I was preparing this talk.
Okay.
Apparently, it's not a device, it's just a procedure. It's not a machine. You can call it
So,
quantum.
do you know what it's doing?
I think what it does is just interacts particles together and then plots the probability distributions over a long period of interactions.
So,
I'll send you the paper.
I appreciate that.
And I found it and I put a link to it there.
Okay.
Because I put the link specifically for myself because I wanted to give myself time later to read it. I had it, I just found those nice neat looking
Yeah,
pictures,
yeah.
which look like a spherical harmonics you'd expect. Any question from students?
So kind of recovered.
Well, very good. Let's thank Mo once again.
Thank you very much.